to you Owen Rambow, who's a research scientist currently at Elemental Cognition. He focuses on natural language understanding and generation. He's published extensively in the top conferences and journals in computational linguistics and natural language processing. His specific interests include both the nuts and bolts of language, such as morphology and syntax, and how language is actually used in context. And he's done state-of-the-art work also in computational modeling of Arabic morphosyntax. He earned his PhD from the University of Pennsylvania under Aravind Joshi, arguably one of the most influential mathematical and computational linguists of the 20th century. And he's worked at AT&T Labs Research and at Columbia University as a research scientist. So please give him a warm welcome.
And thank you. And sorry about the gmail.edu. That's sort of wishful thinking or something. So this is what I'll talk about here. I'll start by just some general remarks about computational language. I will have two quick notes about research I've done, one about studying written dialogue and a second one about Arabic natural language processing. Then I'll go into my main, the main part of the talk about tree adjoining grammar and conclude. So just to start with some terminological issues, we have these terms, natural language processing and computational linguistics. I'm just going to use them as if they were the same thing. Clearly there's some sort of a spectrum going from theoretical to work, purely theoretical work, to pure system building, and the two terms occupy different ends of the spectrum, but to really find the point where they where one stops and the other takes over is hard, so I will just talk about NLP-CL. Just to state the obvious here, computational linguistics is not a subdiscipline of linguistics like morphology of syntax. It doesn't study another aspect of language, rather it is a particular method to studying language, so you can do computational morphology or computational syntax. So why do we even need natural language processing, computational linguistics to study language? Language itself is an empirical phenomenon which we being people interested in language want to study. If we're interested in what I call the nuts and bolts of language, which is essentially what is a grammatical sequence of words and what does it mean, we simply need to know the facts about a language, and that is often kind of hard. I will talk briefly about Arabic dialects, where the facts of these languages are not well known at all. And then if we're interested in how people actually use language, these are by definition empirical issues. We need to study how people use language. And look at these corpora. Now we've had these massive changes since the 1990s when I got my PhD. First of all, the internet has come into being, which means that lots and lots of data is available at our fingertips, addressing both types of studies, the nuts and bolts and the usage studies. And secondly, machine learning has made enormous strides and has provided us tools that allow us to analyze the data and to make predictions from the data. So that NLP, computational linguistics, allows us to collect and analyze linguistic data and thus address our goal of understanding this empirical phenomenon, which is language. So how should we use this? How should we use NLP to study language? I think there are two aspects to it. First of all, we need to understand the phenomenon. Language is not like other, it's not like photosynthesis, it's not like gravity, it's its own thing. We need to understand what it is. And there's a lot of work that has been done in traditional non-computational linguistics, both theoretical and descriptive linguistics, that is directly relevant to us, and that I hope I will show in this talk can help us understand and make progress in computational studies of language. And on the other hand, we need to look at large amounts of data in order to understand the breadth of the phenomenon that we're interested in. So what we want is, we want tools in natural language processing that can exploit both descriptive theory and data. And just a side note that natural language processing is not just relevant to linguistics as an academic discipline. The analysis of language is, of course, crucial for any discipline interested in human behavior, because a lot of human behavior is communication through language. And I want to mention 3 projects at Columbia that I was involved in. A history project with Matt Connolly about analyzing State Department cables. The point here being that a lot of historical archives, starting in the 70s and of course accelerating more recently, are in electronic format, and there's tons and tons of material there. With Desmond Patton and social work, we analyzed tweets among gang-involved youth, in addition to the theoretical interest of seeing how violence spreads through Twitter communication, there was also actually an engineering goal, which was to to enable violence interrupters to recognize when violence might happen in real life outside of Twitter. And there was a very exploratory project with sociology to detect social networks among the Taliban of Afghanistan. So these disciplines also need NLP tools and researchers able to use them. And what I think is interesting is also this perspective that knowledge of NLP tools can lead researchers in these disciplines to ask questions that haven't traditionally been asked in those disciplines. So now a very short note on work I've done over the years in studying written dialogue. There was a lab at Columbia that I headed called WISER, studying written interaction and social relations. And it started with the Enron corpus, which was this energy company that went bankrupt. And as a result of the bankruptcy, the email corpus of the company was released. And it represents a very large corpus of written interactions, unlike almost anything that's available else. And 3 PhD theses came out of it, or are coming out of it. One, how power and gender affect language choice in emails. Vinod Prabhakar on how social networks are represented in narrative texts, Apoorv Agarwal, and how we can use social network information to distinguish personal or business emails. A second related line of research is modeling discourse participants' cognitive state, which is a well-known basis for communication, with Susan Brennan here at Stony Brook having made important contributions. And just before leaving Columbia, I led an effort to create a corpus annotated with source and target belief and sentiment, so who believes what and with what strength of belief, with what commitment, who has what sentiment towards what. The corpus is both newswire and discussion forums, meaning it's interactive, and it's 3 different languages. And going forward, I would like to use this corpus to build on existing work on how language use is affected by cognitive state, and to develop joint models for predicting belief and sentiment, following the pioneering work of the late Jan Wiebe. Now, the second note about Arabic NLP. Arabic is a very interesting language for people doing natural language processing or doing linguistics. First of all, it has complex morphology, including templatic morphology, where the actual stem configuration changes, not just the affixes. The writing system omits short vowels and other diacritics, which carry a lot of the morphological information. So if you're doing automatic processing from written text, this increases the difficulty. Written Arabic is much more ambiguous than English, which already is more ambiguous than German, for example. And then Arabic has what is called diglossia, where there are 2 forms of the language: a high form, which is used in formal communications, written communications, and is not anyone's native language, and what is called the low form, which is a spoken form and traditionally wasn't written at all. And for Arabic, the relationship between these forms is somewhat similar to Latin and the Romance languages around the Mediterranean. So if all the countries where Romance is spoken around the Mediterranean used Latin to write and to do the evening news, that's sort of what you would get in the Arabic world. But what is interesting for us as NLP researchers is that the dialects are now starting to be written because of the emergence of social media, where people just naturally write in the way they speak. We see this in English as well, but in Arabic it has the effect that people are not writing the same variant of the language that we have been studying for years. So there's very little work in Arabic NLP beyond standard Arabic, but there's also very limited descriptive work in linguistics of the dialects, partly because there's so many. There's such a huge continuum from Morocco to Oman. And at Columbia, I was a co-founder with Mona Diab and Nizar Habash of the CADM group, which is dedicated to studying Arabic and its dialects. With my colleague Nizar Habash, we developed a morphological analyzer, which is a direct implementation of the templatic morphology. I don't want to go into details here. And by the way, I apologize. I don't know why that toolbar at the top doesn't disappear, but there it is. And we created a morphological tagger, which sees a word in context, performs an analysis and produces multiple possible morphological analyses. Then it performs multiple tagging tasks for different morphological features such as core part of speech, gender, number, and so on. These predictions are taken together and used to rank the possible morphological analyses, and then one is retained. So this is a combination of machine learning and rule-based morphological analysis, exemplifying my claim that for many problems we need to combine it. The reason we can't just do tagging is that the full tag set is in the thousands, and the quality wouldn't be good enough. And here's a demo. I just want to mention that this particular system is being licensed through Columbia to commercial companies that use it. Currently and going forward, I see the emphasis of my work being on the dialects. The work so far was mainly on Standard Arabic. So we have been developing resources for the dialects, which means hand annotating small written corpora. So small 30,000 words is not, these corpora are not really enough to do machine learning, to do high quality machine learning on their own for each dialect separately. But because there's so many dialects, you can't really do more. The annotation is for a normalized orthography because there is no standard orthography for the dialects, and morphological annotation and glosses into English. And we will use these to develop NLP components, orthographic normalization, morphological analysis, and tagging. And the dialects covered, you see here, Moroccan, 2 Yemeni dialects, Syrian, Iraqi, Najdi, a Saudi dialect, and then smaller corpora for 25 dialects. And these will complement existing work by other groups for Cairene, Egyptian, and Palestinian, and a large Emirati corpus under development. So what do we do with these corpora? Where I think we need to go is to move away from this one language, one NLP system model, because in fact what we have here is a collection of many languages that are closely related, and each of these languages / dialects does not have sufficient resources to create a standalone system. So we need to develop a system based on machine learning that can learn from all of the corpora that we have, that together then end up being a fairly large corpus, and can then analyze any incoming dialect and determine not only the dialect but also the morphological structure of the word. And this kind of work will necessarily again rely on our understanding of the dialect, the morphology of Semitic languages and Arabic in particular. Okay. Now let me move on to the core of this talk, which is about tree adjoining grammar, and I will start with motivation and definitions. So 2 ways of motivating work on tree adjoining grammar. One is there are 2 different ways of representing syntax for computational purposes. One is a dependency structure, and the other the phrase structure. These are both types of trees, and they differ in the label sets. They have, in a dependency tree, all the nodes in the tree are labeled with terminal symbols from the language, which means the words from our sentence. Whereas in a phrase structure tree, only the leaf nodes are labeled with the words from the sentence, and the interior nodes are labeled with the disjoint alphabets and non-terminals. Now, dependency is useful for natural language processing because it provides a more abstract representation than phrase structure, and thus allows for an easier transition to lexical semantic interpretation. And furthermore, since it only contains words, it fits very well with word-oriented models of the types that have been developed recently. On the other hand, phrase structure is useful for linguistic description theory because it gives us a more fine-grained descriptive tools. For example, we can have something called a VP, and this allows us to formulate theories better. So the question is, can we have a system that combines both phrase structure and dependency structure? And a basically very closely related motivation is lexicalization. We want lexicalized grammar so that we can express syntactic properties in the lexicon and tie them to words, which is what corpora are made up from. So what does lexicalized mean? A formalism is lexicalized if every elementary structure contains at least one terminal symbol, And we cannot lexicalize a context-free grammar in a linguistically interesting way. So context-free grammars, of course, were the grammars developed by Chomsky in the 60s, or co-developed in the 50s, I guess. But they are actually not a good way to describe syntax if we want to have a lexicalized grammar. So can we have a grammar formalism that is lexicalized? And the answer is yes. We can say yes to both of these questions. The answer is tree adjoining grammar, developed by Aravind Joshi starting in the 70s. The elementary structures are phrase structure trees, and we have two operations, substitution and adjunction. Substitution just takes one tree, which is rooted in a non-terminal symbol A, and pastes it at the bottom of another tree that has a frontier node labeled A. Here are linguistic examples. We have a tree for likes, transitive verb likes. We have a tree for John and for Lynn. We can paste John and Lynn into the two frontier nodes labeled NP on likes, and we get the tree for John likes Lynn. Adjunction is a more interesting operation. It's essentially the same thing, except the second tree is inserted into the middle of the first tree. We remove the subtree rooted at the node where adjunction is being performed. We paste it at the bottom of the auxiliary tree we're joining in, and then we insert that at this node, and we get this effect here where the adjoined in tree is inserted in the middle of the receiving tree. A linguistic example below here, we continue with John likes Lynn, and we want to add an adverb. We can't do that at this point because the adverb has to go between John and likes. We can't do it with substitution, I mean. So we use this adjunction operation. We have this really tree that's rooted in VP. We adjoin it at this VP node, and as a result, we get John really likes Lynn, and the really is inserted in the middle of the likes tree. So this is a full derivation here, and what's important about this derivation is that we can record the steps we performed in the derivation, and what we get is this tree here. We start with the like tree, we substitute the John tree at the node at node 1. These numbers here are a particular convention for labeling nodes and trees, very generic. We substituted Lynn at 2.2, and we adjoined really at 2. Now we can replace these somewhat obscure node labels with linguistically meaningful labels. We know that this is the subject position, this is the object position. We know that things adjoined to VP are adjuncts, and we get this tree over here. So what you see is that we derive a phrase structure tree, but the derivation itself is recorded as a dependency tree. So to summarize up to here, we have a lexicalized formalism. Each elementary structure of the grammar has a word attached to it. And when we perform a derivation, we get a phrase structure tree, and we get a dependency tree at the same time. So all these properties make tree adjoining grammar really appealing for computational purposes. Now, to get a little bit into details of how this works with language, let me talk about tree families. So for a verb like eat, for example, we will have different trees for Tom eats beans, or Tom eats, or beans were eaten, or what did Tom eat. And notice that I'm going to factor out the auxiliaries will and are and have and so on. They come with their own trees. So I'm really interested in these trees here, and the question is, what sort of trees do we expect for a given verb? Well, we can analyze it according to different dimensions of syntactic analysis. The first one is the subcategorization. So we have intransitive verbs that only take a subject, transitive verbs that take a subject and object, and ditransitive verbs that take a subject, a direct object, and an indirect object. Then we have an orthogonal dimension, which is voice. We can have an active or a passive tree. Of course, if we don't have a direct object, we can't have a passive tree. We have a third orthogonal dimension, dative shift. If we have an indirect object, we can either express it as two noun phrases or as using the to prepositional phrase. Again, of course, this only works if we have ditransitive verb. And then we have various types of WH movements. So we can ask questions like who ate beans, the subject, what did Tom eat, the object, or we can form a relative clause. So this would be the beans which Tom ate. And this structure up here on NP tells us that this whole tree will be adjoined to a noun phrase. So we can define trees in a tree adjoining grammar using a vector of syntactic dimensions. So these are the trees we just saw. they have different subcats, different voice, different data shifts, different WH movements, and sometimes the value will be non-applicable because dative shift doesn't apply to transitive verbs. And we call those trees that are in the same, that have the same subcat a tree family. And this kind of representation of the trees, which are the elementary structures of our formal grammar, we will resurface. Now, one reason why tree adjoining grammars caught the attention of linguists was the treatment of long distance movement. So if we have a structure with an embedded clause, one thing we can do, so we want to derive the sentence, Mary thinks Tom eats beans, we can adjoin the matrix clause, the things clause, to the root node of the eats clause. So this here, this tree will be adjoined there. Since it's at the root node, we get the red tree, the matrix clause, entirely above the blue tree, the embedded clause, just as we expect. But what's nice now is, if we want to derive the sentence, what does Mary think Tom eats? We use exactly the same thinks clause, and we use the tree that we developed for the monoclausal question, what did Tom eat? And then we do the same adjunction at the S level here, and because we're now inserting in the middle of the tree, we have this effect that the parts of the blue tree move apart from one another. And we get this what is termed long distance movement in other accounts. We have a record of the fact that whatever noun phrase is inserted here is a direct object of the embedded verb and is not an argument of the matrix verb. And we don't need to express this this long distance effect explicitly. And this led Tony Kroc and his student Bob Frank to formulate this model of tag-based syntax. This is formulated in terms of syntactic theory of the 80s. I beg the pardon of any theoretical syntacticians in the room here. But basically, if we want to have a theory of syntax, we have to have a set of principles and parameters that are restricted to clausal deep structures and that restrict how things move around to create clausal surface S structures. And then the formal derivation derives multi-clausal structures. In contrast with the situation of Chomsky theoretical syntax, so here's the 80s model, government and binding, where the principles and parameters had to restrict everything, not just within a clause, but across a whole sentence. This means that this set of principal parameters will be much smaller than this set because a whole part of theoretical syntax has been taken over by the formalism. That is the theoretical linguistic promise of tree adjoining grammar. Now, getting back to practical issues, where do tag grammars come from if we want to do NLP with tag? So either we can derive them using linguistic theory, that's what I just talked about. We can create them by hand. There was a project at Penn in the early 90s doing just that. But what we do nowadays is we extract them from annotated tree banks, such as the Penn Tree Bank. There were two main efforts, and we use the one by John Chen, which is the basis for all work reported in this talk. And we can also use something called a metagrammar, which has similarities to work done in HBSG. And just because I find this really interesting, I'm going to have one slide on German. So in German, German has much freer word order than English, so we can have a sentence like, in English it's yesterday Hans tried to give it to the children. In German, it is broken up into 6 different fields, matrix clause embedded, matrix embedded, matrix embedded. And this is a problem for tree adjoining grammar because when you do an adjunction, you split the 2 trees into 5 segments, 1, 2, 3, 4, 5, and here we have 6 segments. So we can't just use simple tree adjoining grammar to derive this sentence in German the way we want to. I'm hoping you won't object to this German sentence. So for German, we need operations more powerful than simple adjunction, and I don't want to talk about work I did 25 years ago, but the kind of structures I proposed is taking trees and relaxing the dominance constraints that trees that are part of trees to indirect dominance constraints so that this VP doesn't immediately dominate this VP, but stuff can intervene here. And this can then derive the German data. But it also interestingly helps with certain interpretations of derivations of English cases where we have a combination of WH movement and raising. And if you're interested in this, I'm very happy to talk more about it. Now moving on to supertags. So terminology alert, this syllable tag has two different meanings now, which is confusing. On the one hand, it's an abbreviation for tree adjoining grammar. On the other hand, it's an English word that means label. This has been used in NLP for a long time, such as part-of-speech tags. The part-of-speech tag is a tag that we associate with words and that expresses what the part-of-speech is. So in Mary likes beans, Mary is a proper noun, likes is a verb, third person singular, and beans is a plural noun. And this /NP part, that's the lowercase tag. A super tag, here super means sort of extended tag, same idea, but the label we associate with words is not a part-of-speech tag, but a tree from a tree adjoining grammar. And therefore it encodes the complete syntactic information that we need about this particular word. And by the way, it does not encode morphology, which is just a choice that was made. And depending on the definition of the tree adjoining grammar, the tag set now can be between 500 and 5,000 tags. So it is a much bigger tag set because there's much more syntactic variation than morphological variation in English. And the term supertagging then refers to this process of assigning a tag to each word. And what it looks like here, if we have the beans were eaten, and we have these three trees in our grammar, well, this is a passive sentence, so we need to choose for this eaten T58, which is this one over here, where the direct object has been moved into subject possession. Whereas Mary ate the beans, standard transitive, we have to choose T27. So this /T27, this is the result of supertagging. Okay. Now, the key idea that the work I'm going to present is based on is the idea that supertagging is almost parsing. The thesis of Srinivas Bangalore in the 90s, and the idea is that if we know the supertags, there's very little ambiguity left. And in fact, we have shown that if you have the gold supertags, you can do the parsing task with 98% accuracy, which especially at the time was way beyond the state of the art. What this means is that parsing, which is a structural problem, is reduced to tagging, which is a sequence labeling problem, which computationally is an easier problem, so that's appealing. So now let me go into the core computational experiments that I will present here. There are three experiments. First, an initial effort with Alexis Nasser in Marseille about using probabilistic context-free grammars, and then more recent work with Bob Frank and his group, who's in the linguistics department at Yale, a shift-reduced parser and a graph-based parser. For the probabilistic chart parsing with tree adjoining grammar, we represented tree adjoining grammars, the trees in the tree adjoining grammar, as finite state machines. And then we did non-lexical probabilistic chart parsing, non-lexical meaning that we dropped the words in the sentence and replaced them by their supertag. So for instance, if we have this tree adjoining grammar here with just 4 trees in it, this tree here, which is a transitive verb tree, gets replaced or gets represented by this finite state machine. We traverse the frontier of the tree. We encounter this first noun phrase, non-terminal. The only tree that we can put there is T4, so we have a transition on T4. The next thing we encounter is a head, so we have a transition on the head. The next thing we encounter is this NP substitution node. We have a transition again on T4. But then we have this VP node, and we have 2 trees that we can adjoin to that VP node. So we have these 2 self loops on T30 and T28. So this is a straightforward way of transforming a grammar into a set of finite state machines. And once we have these finite state machines, we can use them in a chart parser in a fairly standard way. A lot of work has to go into estimating the probabilities and, in fact, defining the probability models that we want to have, how to model this adjunction in particular, because this adjunction is not independent of that adjunction. But I will not go into detail. The experiments we did consisted of following the proposal by Bangalore in '96, is first a super tagging phase and then a parsing phase. For the Supertagger, we used a maximum entropy model, and the parser was, as I've been saying, a probabilistic chart parser. A chart parser optimizes over all possible parsers and in fact represents all possible parsers. As I said, the parser doesn't see any words anymore, only supertags, but the parser does enforce the grammaticality of the derivation it finds with respect to the underlying grammar. So if we have a linguistically motivated grammar, we can be sure that this system will give us a derivation that this grammar actually allows. What are the results? As I mentioned, if we have gold supertags, supertag accuracy 100%, the unlabeled parse is nearly 98%, the labeled parse is 97%. So unlabeled means we don't care about arc labels. Is it a subject, is it an object, is it an adjunct? Labeled parse means we do care about it. Now in our actual experiment using our maximum entropy supertagger, the supertag accuracy drops to 86.9%, huge drop. Compare that to part of speech tagging, which is 90, or at the time was 97, now is 97.5, because the tag set is much smaller. So supertagging is a hard problem, and our accuracy drops considerably to 86.7 and more for labeled parse. So this was encouraging in the sense that we are getting results here that are not terrible, but the question is, what if we improve the parsing, the supertagging accuracy? Will in fact the parse accuracy improve? And then happily enough, the deep learning revolution happened, so we could make progress in supertagging. As I assume you know, deep learning means the use of multi-layer neural networks. It has had a massive impact on natural language processing for two reasons. First of all, it is a more powerful machine learning mechanism and often simply produces better results on similar data compared to other machine learning algorithms such as support vector machines. What I think perhaps even more important is the fact that it has enabled word embeddings. So a word embedding is an encoding of words, so not lemmas, but inflected words, as vectors of real numbers, and these vectors represent a context in which the words occur in corpora. Since these are derived using deep learning itself, but this process is unsupervised, meaning that we don't need to prepare corpora in any way. We can just feed existing corpora to a program, and we get word embeddings out of it. And this means that people like Google, companies like Google, can literally use billions of words to derive word vectors, giving us extremely powerful representations of words, both in terms of their syntactic context and their semantic context, depending a little bit on which algorithm we use exactly to derive the word embeddings. So here's an example of the kind of things we can do. If in the training data for our supertagger we saw tossed was T45, we can make this prediction. If we never saw the verb chuck once in our training corpus, basically we have very little chance of making this prediction of the fact that chucked gets the same supertag as tossed here, because it has the same syntax. In fact, it has the same meaning. But if we have word embeddings, the word embeddings for tossed and chucked will look similar and will allow us to make this leap. So we can handle unseen data much better. So the experiments here, the first run of experiments are published in Kasai et al. 2017. We have a new supertagger, which is an end-best supertagger using bi-directional LSTMs, a standard deep learning architecture for tagging tasks. We also changed the parser. We use a neural parser based on MALT, which is a greedy shift reduced parser developed by Nivra et al. For dependency. This emoji here I use to indicate citations where I'm not a co-author, just to make clear what is not my contribution. Citations with et al. Where I'm not a co-author. The neural parser uses embeddings of supertags, but it doesn't use words. In this respect, it's similar to the earlier experiment with the chart-based parser, which also didn't use words. However, unlike the chart-based parser, this parser does not enforce grammaticality because it's greedily making attachments. So at the end, we are not certain that the derivation proposed actually is a valid tag derivation. And in order to address this last problem, we do one other thing, which is we filter the supertagger through the chart parser to get a better tagger. What does this mean? So the deep learning-based supertagger produces n-best output for each word, so 16 possible tags for each word. We feed this to the chart parser, and the chart parser will give us its best parse, which is associated with a sequence of supertags. So that sequence of supertags has a property that it is guaranteed to form a grammatical derivation in our grammar. So what are the results here? The first result, we keep the chart parser from the previous experiment and just switch the supertagger. The performance of the supertagger goes up by 2.5%, and as we hoped and expected, the performance of the parser goes up even a bit more, 3.5%. So this validates our hypothesis that, at least with this chart parser here, if we improve supertagging, we improve parsing. So that was encouraging. We then switched to the neural parser based on deep learning, same supertag accuracy because we're using the same supertagger, and we were surprised to see that in fact the parse accuracy hardly went up, just a very little bit. So given this level of supertagging here that the neural supertagger can provide, the chart parser does as well as a neural network-based parser. But then we used this supertagger I mentioned at the end of the previous slide, where we ran the output of the neural supertagger through the chart parser to get a sequence of supertags that is guaranteed to be a full derivation, but then used the neural parser, and sure enough, the S-tag accuracy went up a little bit more, the supertag accuracy, but the parse accuracy went up even more by 0.7% in both labeled and unlabeled. So the fact that here we have a sequence of supertags that actually is guaranteed to be a valid derivation really helps us in the parse. So as we saw, the neural network parser that we used here made only a small impact. The question is, are there other neural parsers we might want to use? So in another series of experiments, we switched to a different parser. Before doing that, we improved the supertagger because there had been all these developments in deep learning over 1 year, of course. So we added, in addition to giving the word as input, we encoded the word as a sequence of characters. This helps for really rare words. This helps for morphological variants. And we added high-rate connections between layers, as has become common. The parser we do now includes words as inputs, so it takes both supertags and words. And the parser is a graph-based parser following the work of McDonald et al. And what a graph-based parser does, it predicts the probability of the governor node for each node, and then and we do this following the biaffine approach that Dozat and Manning did for graph-based parsing. And then we use a heuristic to choose the best tree given the information of what the best governor is for each node. So this algorithm is computationally more complex because we have to compare each word in the sentence to each other word as compared to the previous neural parser, which is just a greedy parser, goes left to right. Here's the results. So using the neural supertagger and the new parser, first of all, the supertagging accuracy went up yet again. Unfortunately, I can't tell you how the effect was on the chart parser. The suspicion, of course, is that it would also have gone up. But using the new parser, the results are the best results we have so far. The asterisk here means that for technical reasons, I'm reporting on a different section, but the results on sections 23 and section 0 were always similar up to 0.2 points. Now, the disappointing thing was, in the next experiment, we turned off the supertagger and just ran the parser. And what we got was an improvement in performance. So what this means is the parser is taking the words directly. We aren't using any supertags. We're not using any tree joining grammar information at all anymore. And the whole point of this exercise is to show that linguistic information is useful and can help in parsing. So this was a disappointment. So we looked at the parser again and defined a joint prediction model. So instead of just predicting what the governing node is, we also now predict for each word what the supertag in the part of speech is. So in the first neural model, the supertag was an input to the prediction. Now the supertag is an output to the prediction. So in this diagram here, you see that for the word John, we're predicting the governor, we're predicting the label, but we're also predicting the supertag and the part of speech. And during the training phase, when we have all this information, these predictions will affect the weights that the system learns in the actual neural model. And even though we don't feed the supertag into this joint model, it knows about supertags during the training phase, and it performs better, a further increase by 0.6% or 0.5 for labeled. And interestingly, the supertagging accuracy is competitive with the neural supertagging model that was trained specifically just to do supertagging. So this was a relief that supertagging still helps, though not as an input to the parser, but as an output from the parser during training. And this is a nice reminder that with deep learning, the kind of pipeline models you think of initially might not be the right ones to pursue. And there are different ways of incorporating linguistically informed models into the machine learning. Now I want to look a little bit deeper in, how much time do I have left?
We started a little bit late, but we can go 5-10 minutes, and then we can go for questions.
Okay. What is the linguistic knowledge we're using giving us? Actually, can we show that we're actually getting something out of this? So the first point I want to make is about the supertag embeddings. The first parser we use uses not so neural models. You can't feed it as a string like T27. You have to feed it numbers. So you need an embedding of supertags. There are different types of embeddings possible. A one-hot embedding, which is just a vector as a length of your grammar size, and it has a 1 in exactly the position that corresponds to the tree that the supertag represents. The glove model is like a word embedding, where we trained it on a sequence of supertags that were on the corpus that we use for supertagging training. Then, since supertags in fact correspond to trees one-to-one, we developed a model of a recursive tree embedding and used the structure associated with the tag to represent the tag. And then the fourth is we use the features that I talked about earlier to represent the supertag, and these are these features like subcat and voice and dative shift and WH movement. So these dimensions define the embedding. And here's a result. If we take the gold supertag, the atomic representation, meaning the one-hot embedding, is the best because it just tells us this is the right supertag, use it, the parser learns that, and can derive the right parse. For the labeled parse, the situation is very different. Well, not very different, but different. Namely, the linguistic features perform slightly different, better at this point. And the interpretation here is that by having a vector that represents explicitly the linguistic content of the supertags, the parser can learn to pay attention to certain dimensions as needed in different contexts. So for example, if we have an intransitive verb, don't look for an object to its right. Now, truth be told, the improvement is fairly small. Still, we're very happy to see this. The second trace of linguistic knowledge in results is not my work, but it's the work done in the group of Bob Frank, with whom I did the work I'm talking about here, in a very recent paper on questions. So anyone who's worked on parsing for applications knows that questions are really hard to parse simply because the Wall Street Journal corpus that we use to train our parsers has very, very few questions. On the other hand, questions are really important for many applications, question-answer systems and so on. So the idea here was to use a small corpus of questions which have been supertagged by hand but not fully syntactically annotated, so that this annotation would be easier than full syntactic annotation. And they annotated 350 sentences. In comparison, the Penn Tree Bank training corpus has nearly 40,000 sentences. So a very small corpus. In order to make it visible in the training phase, they multiplied it 35 times. We just repeated that data 35 times. And obviously, in order to evaluate the parsing accuracy, they annotated a test set with a full syntactic structure, but they use it only for evaluation. Here are the results. When we skip the results on the full pen tree bank, they aren't as interesting. We're going to look at the results on the question corpus over here. And there are two dimensions. First of all, we can use a gold supertags, or we can use predicted, and we can use predicted trained on the pen tree bank only, or the predicted supertags trained on the pen tree bank and those 350 extra sentences. So first of all, and then we're going to look at these two different embeddings that I already just mentioned, the atomic or one-hot embedding and the linguistic feature embedding. And if we look at gold supertags, earlier the atomic embedding performed best. Now it doesn't. In fact, the linguistic feature embedding performs much better because the parser hasn't seen questions. So even if it's fed the correct supertag for this question, it doesn't know what to do with it. On the other hand, it can use the linguistic features to abstract the question part from the rest of the supertag, and it performs a surprisingly high accuracy. This number is partially so high because the question test set here contains fairly short sentences compared to the standard pen tree bank. Now, what I thought was particularly nice in this work is that when they used the predicted supertag trained only on the pen tree bank, so not using this extra data sets they annotated by hand, using the linguistic features also gave a big boost of 4 percentage points. It's the same reason as over here, that it could exploit, it could divide out the question part of the syntax from the other parts, such as transitivity or voice. And then as expected, if we train on the small corpus, we get a boost for both types of embeddings, but the boost was even bigger for the linguistic feature embedding. So this is a nice documentation that these linguistic features are doing something, and they're doing something in particular for syntax which has not been seen in training. And the third type of linguistically interesting result I would like to discuss is unbounded dependencies. TAG is an elegant analysis of moved and unbounded dependencies, things like subject-relative clauses, an instrument that measures depth. Object-relative clause, the book which you read. So the star here is the original location of this which. So the direct object, which is represented by the which, is in a non-standard location in English. Or an embedded subject, this is a long-distance case I talked about earlier. The responsibility which the government said lay with the voters. This which here is actually the subject of this lower phrase and separated by the matrix clause, or by this clause, the say clause. So we expect tree adjoining grammar to help with this because this is exactly where it provides nice analyses. And we use the unbounded dependency corpus to do our tests, which contains a bunch of sentences of this type. We use the corpus only to evaluate, not to train. We do not do any retraining. There are different types of constructions in this unbounded dependency corpus. I'm just listing some interesting ones. So for subject-relative clauses, and I'm listing here 3 other parsers which were reported in that 2009 paper. As a result, these are parsers that are fairly old now, so to some extent we're comparing to not state-of-the-art parsers, and I acknowledge there's a bit of a problem here. We see that for subject-relative clauses, the mult parser, which is a greedy left-to-right parser, does perfectly well, in fact better than our parser. Why is that? Because in subject-relative clauses, the word order is actually just as expected. The subject is to the left of its verb and so on. There's no fancy syntax happening. But if we go to object-relative clauses, we see a big drop in performance of all the parsers, whereas only a small drop for our parser. And then the embedded subject, that is where the adjunction in tag separates the two elements that are now related in a long-distance relation. There are massive drops for the other parsers, but ours has, well, a drop, but not as big. And overall, we fare better than these others, just as we'd expect, because we are modeling these linguistic phenomena explicitly. So to wrap up this section on tree adjoining grammar allows us to represent detailed syntactic information in our grammar, and it can provide a link to existing syntactic theory. But it can also be used directly to create dependency parsers, which is what we often want to do in natural language processing applications, where syntactic parsing is never the last step. We want to move on from there to semantic interpretation. And the experimental results show that supertagging is useful for parsing, either as input to the parser or as output from the parser during training. And we have shown that the linguistic information that tree adjoining grammar can represent explicitly can be leveraged to improve performance for rare syntax or for complex syntax. And to wind up the whole talk, let me say language is important. Beyond linguistics as an academic discipline, computational models are crucial to develop comprehensive models of language across disciplines. There is too much data to analyze by hand, and this data should not be ignored. It is very important to both to descriptive linguists, theoretical linguists, computational linguists, and to people in other disciplines as well. And therefore, we need computational models of language which can both incorporate linguistic insight that exists and that is developed, and that can handle these vast amounts of data. And I have suggested that tree adjoining grammar is one such framework that allows us to play on both of these registers. Thank you.
Okay, thank you very much. I think we'll take about 5 to 10 minutes for questions. Owen, I'll let you go ahead and field your questions.
Yeah, so thank you. I'm not sure if what I have is a question or just a half-baked thought. So one thing I found interesting was when we were talking about the note 2 on Arabic, I understood that sometimes we were talking about the dialects, and the one thing you said was kind of we shouldn't look at those in isolation. This is kind of like a whole system that we have to understand. And so if we understand the system, each dialect is just a minor variation of the overall system. Did I understand that?
Yes, exactly. Yeah.
Yeah. I mean, this is neat because I mean this is basically just it's a smaller version of what the linguistic promise is, right? The promise of linguistics is that if we just figure out how language works, every natural language is just a dialect of that underlying thing.
Yes.
But clearly we have not succeeded in scaling that up to that level, right? So I was just wondering if you could kind of like say a few things about why you think it is currently feasible to handle that in like this smaller domain with things that we would actually consider dialects, but it starts to fall apart when we try to basically go and cluster things together that we would rather classify as separate languages to actually the same thing.
So I think the Arabic case is a good case to take on at this point, because so you made the point that linguistics in general sees language that way. The Arabic dialects do have a lot in common. They all have the same type of morphology. They have variance in word order. They have shared vocabulary and so on. So we don't have to deal with the entire variation of human language all at once. That's one advantage. And I think, I don't know if there's a difference, maybe you can tell me, but what I think we have to deal with, on the other hand, is a non-discrete nature, that we cannot consider Taizi and Sanani Yemeni as two different languages, because if you go halfway between the two cities, you'll find something that looks like it's a halfway between the two dialects. So that this transitionary aspect is part and parcel. And people have looked at dialects, for instance, the Dutch-German border. There's well-known word order differences between Dutch and German, and these word order differences don't follow the political border, but they also don't follow the difference in words. So in the Netherlands, you'll use different words, and there might be a word boundary which is not the same as a syntax boundary. So dialectologists knows all this and so on, and we see this in this Arabic data, and we will need to exploit that. So I think that the problem is both easier to handle because of the similarities between the dialects, and perhaps harder because we have to deal with this micro variation. It's part of the project. Does that address your question?
I'm interested in the, if you go back to the results you had a number of them, but that compared the linguistic features or the chart, the neural to the, and there was the results were very similar in terms of their accuracy.
Yes.
Maybe one was a bit better than the other. But I was wondering if you looked at the errors at all to see if the errors were qualitatively different in the two cases.
Yes, that's a good question, and a student did, and I don't have the answer in my head. I apologize. Yeah. Yes,
Okay.
that is a relevant question. We expect, if we use linguistic-based features, that certain things that we can identify that it just got one dimension wrong, and therefore the parse failed because of that. Yes.
Okay.
I guess a mundane technical question. I mean, so how big is big? I mean, so big to some extent is in the eye of the beholder. To me, it means you've crossed sort of some technical boundary where just the sheer volume, the software or whatever you need to process it has crossed the level. So what scale are we working at here?
Yes, so the corpus we're working with for training the supertagger and the parser is 1 million words. It's a Pentry bank, which is no longer big, which was big 10 years ago, perhaps. But we are exploiting other corpora as well. We're using the word embeddings, for instance, the way everyone does these days, which are trained literally on billions of words. And one of the experiments that I want to do in the future is using self-training, where we annotate an unannotated corpus, perhaps using different supertaggers. We have this chart-based parser that can guarantee a sequence that's good. We have these very high-performing neural supertaggers now, getting 90.8, and we have several. We can do an ensemble, so we can self-annotate very large corpora and also corpora outside the domain of the Wall Street Journal, and train supertaggers on that self-labeled data. And similar experiments have shown that you can thereby improve performance on that out-of-domain data. And this is something that supertags are particularly good at. And it's something a little bit like what the question experiment did, because they just got supertags for the question domain, which is sort of like a different domain from the Wall Street Journal, and that enabled an improvement in performance there. So there, I think, because that is then unsupervised, we'll also be working with much larger corpora there. And the large corpora then allow us to, for example, eliminate sentences that are hard or something like that, or where the supertaggers disagree, or we can use heuristics to achieve good self-labeling.
Yeah, so one thing that I find interesting about the supertagger approach is that it kind of brings back syntax to just the land of regular string languages, right? Because you basically have your abstractly speaking, even if it's a neural supertag, at the end of the day, you have some kind of finite state machine that's probabilistically assigning those tags to words as it sees them. And so I'm just wondering if anybody's trying to kind of like actually study basically that supertagging problem in terms of the actual string languages that are defined this way. So basically, for instance, you're not going to need modular counting in those things, right? So it's actually going to be subregular, because you're probably not going to end up with a supertagging model that somehow needs to make even odd distinctions or something like that, right?
Yeah.
So it looks like it's probably going to be a very weak subclass of finite state machine that you actually need there. And I'm wondering if this is something that could be exploited in the future.
You mean to restrict the output of these supertaggers when
Yes.
they're making?
Basically,
Yes,
narrow
yeah.
down the hypothesis space to you have to end up with something that sort of looks like this.
Yeah.
And then going back to the first question that I had, basically, well, maybe what we can do is we can start doing things like bootstrapping the supertagger for English over to a supertagger for whatever, Navajo.
Yes.
If we just knew
Yep.
how these things hang together, and we only need very little data to infer what the translation should be.
Yes. So, or a question to you: this idea of using this supertagger followed by the chart parser, in a sense, is doing that. It's eliminating sequences that don't conform to a particular grammar. This grammar is actually, in fact, the context-free grammar, so it's still fairly powerful, but it is eliminating certain sequences that are not that are impossible according to the grammar. So this could be pushed further. That's a good idea. And yes, the multilingual aspect, I didn't mention this, but I think there's great potential here, because the representation of these trees in terms of these syntactic features. The syntactic features, the ones I showed in particular, would be essentially universal. They're transitivity, the dative shift construction is very particular to English, but there are different variants of realization. There are relative clauses in most languages and so on and so forth. So we could transfer this kind of data from one language to another language, and even in a language where we have almost no annotated corpus, if we can by hand create a grammar that refers to these dimensions, we might be able to bootstrap, as you say, a tagger for Navajo in this manner, and sort of using knowledge about language in general that we've learned from the English corpus. Yeah. There has been recently some interest in cross-language projection for parsing, but none of that has used Supertags. So I think there's a clear research direction there.
Okay, I think we should thank our speaker again.